Hello, dear friends. Today, we're embarking on an exciting journey through the vastness of our solar system, our cosmic home. It's a unique, dynamic, and incredible system formed billions of years ago, still holding countless mysteries. We'll explore its structure, its place in the universe, and why studying it is so crucial. Get ready for a captivating dive into science and history. Let's begin. The solar system is a grand gravitational mechanism centered around our star, the Sun. It comprises 8 planets orbiting our star, along with over 200 known moons, countless asteroids, comets, and interplanetary dust. These objects are bound together by gravity, forming an intricate and harmonious structure. Around 4.5 billion years ago, a vast cloud of gas and dust began to collapse under its own gravity. A dense core formed at the center, the precursor to our Sun, which soon ignited with thermonuclear reactions. The remaining material formed a spinning disk, from which planets, moons, and other bodies gradually coalesced. This process is key to understanding how star systems form across the galaxy. Our solar system serves as a unique laboratory for studying the processes that shape other star systems. Our solar system resides within the Milky Way galaxy, which contains an estimated 100 to 400 billion stars. We're situated in the Orion Arm, or Orion Spur, about 27,000 light-years from the galactic center. This is a relatively quiet region, which likely played a significant role in allowing life to arise. So, what exactly are these spiral arms? They are major structures within spiral galaxies, bright, winding regions filled with star-forming areas, gas, and dust. Being located away from the major arms, like Perseus and Scutum Centaurus, provides us relative safety, as we're far from the galactic core, where activity is much more intense. The solar system orbits the galactic center at a staggering speed of about 828,000 kilometers per hour, or 514,000 miles per hour. However, completing one full orbit takes an estimated 225 to 250 million years, what's known as a galactic year. The last time our solar system was in this part of the galaxy, dinosaurs roamed the Earth. It's incredible to think that if you could view the Milky Way from afar, our solar system would be just a tiny, barely visible speck among billions of stars. Yet, it's on this tiny speck that life arose, a phenomenon we haven't yet found anywhere else in the vast universe. Let's take a moment to reflect on how our understanding of our place in the cosmos has evolved. In ancient times, people believed Earth was the center of the universe. This was based on the geocentric model proposed by Ptolemy, which remained the dominant view in astronomy for about 1,500 years. According to this model, all celestial bodies, including the sun, moon, and stars, revolved around the Earth. However, the 16th century marked a pivotal moment in astronomy. Nicholas Copernicus, a Polish astronomer, proposed the hypothesis that Earth was not the center of the universe, but simply one of the planets orbiting the Sun. This discovery laid the foundation for the new heliocentric model. Naturally, this idea faced resistance, as it challenged centuries-old beliefs about humanity's place in the cosmos. Copernicus paved the way for a revolution in astronomy. The next key phase came thanks to Galileo Galilei in the early 17th century. Using an improved telescope, Galileo was the first to observe the moon in detail, seeing its craters and mountains, contradicting the idea of a perfect celestial sphere. He also observed the phases of Venus, providing strong evidence for the heliocentric model. These discoveries confirmed Copernicus's hypothesis and forced a fundamental rethinking of astronomy. Isaac Newton, in the late 17th century, completed this shift with his laws of universal gravitation. He explained why planets move in orbits around the sun. Newton demonstrated that gravity is the force holding all celestial bodies, from the moon to the distant planets, in their orbits. His work became the foundation of classical mechanics and allowed for much more accurate predictions of planetary motion. From the late 19th century, and especially in the 20th, the era of practical space exploration began. In 1969, the Apollo program successfully landed humans on the moon. And with the development of spacecraft and powerful telescopes, humans began actively exploring not only nearby planets, but also the distant corners of the universe. The Hubble Space Telescope, launched in 1990, opened new horizons, providing astronomers with incredibly precise data about stars, galaxies, and other cosmic objects. Thus, the journey from the geocentric model to our modern scientific understanding of the cosmos was paved with crucial discoveries and revolutionary ideas. Having reviewed these milestones in astronomy and our cosmic perspective, let's turn our attention to the planets closest to the Sun, known as the inner planets. These are Mercury, Venus, Earth, and Mars. They form a unique group of terrestrial or rocky bodies, distinctly different from the giants of the outer solar system. Let's start with the small but fascinating planet, Mercury. Mercury is the closest planet to the Sun, and nearly everything about it is dictated by this proximity. It orbits at an average distance of about 0.39 astronomical units, AU, meaning it's less than half the distance from the Earth to the Sun. Since 1 AU is about 150 million kilometers, 93 million miles, Mercury averages just 58 million kilometers, about 36 million miles, from the Sun. This makes it the first stop in our planetary tour. Mercury is the smallest planet, with a diameter of about 4,880 kilometers, 3,032 miles, roughly 2.5 times smaller than Earth's diameter. Despite its tiny size, it's denser than many other planets due to its large iron core. Mercury completes one orbit around the Sun in just 88 Earth days. That's its year, the shortest of all planets. But its day, or one rotation on its axis, lasts 59 Earth days. However, due to a complex interplay between its rotation and orbit, one solar day on Mercury, sunrise to sunrise, lasts a full 176 Earth days. This unusual phenomenon is due to a 3.2 spin-orbit resonance. Mercury rotates on its axis 3 times for every 2 orbits it completes around the Sun. This resonance was caused by tidal forces that gradually slowed the planet's rotation. Mercury lacks a significant atmosphere, leading to extreme temperature swings between its day and night sides. The sunlit side can reach scorching temperatures of 430 degrees Celsius, 800 degrees, hot enough to melt lead, while the night side, receiving no solar heat, plunges to a frigid 180 D, 290 D. This temperature contrast is one of the most extreme in the solar system. Mercury is mostly metal. Its core takes up about 75% of the planet's diameter, making it disproportionately large. This core is primarily iron and likely partially molten, responsible for generating a weak magnetic field, about 1% the strength of Earth's. Still, even this weak field creates a magnetosphere that interacts with the solar wind. The planet's outer shell, or crust, is very thin, around 20-30 kilometers, 12-18 miles. Mercury's surface is heavily cratered from intense asteroid and meteoroid bombardment during the early solar system. One of the most impressive craters is the Colossal Basin, with a diameter of over 1,550 kilometers, 960 miles. The impact that created it was so immense it caused chaotic terrain to form on the opposite side of the planet. The study of Mercury began with the Mariner 10 mission in the 1970s. This spacecraft provided the first detailed images of the surface and discovered its magnetic field. But a true revolution in understanding Mercury came with the Messenger mission, which orbited the planet starting in 2011. It gathered data on surface composition, measured the magnetic field, and revealed numerous geological features. Mercury is a window into the early solar system. Its surface has remained largely unchanged for billions of years, preserving clues about the processes of planetary formation. Its unusual structure and motion provide scientists with insights into gravitational interactions, the influence of stars on nearby planets, and the cooling processes of planetary cores. Next up is another enigmatic planet, Venus, where conditions are so harsh, it's rightfully called a hellish world. Venus is the second planet from the Sun and Earth's closest planetary neighbor, remarkably similar to our own planet in size and mass. It's often called Earth's sister planet, but the similarities mostly end there. Venus is a veritable cosmic hell, dominated by unbearable heat, sulfuric acid clouds, and atmospheric pressure capable of crushing any terrestrial probe within minutes. But behind this extreme environment lies a story that could tell us how Earth's fate might have unfolded if our planet's balance had been disrupted. Its diameter is about 12,100 kilometers, 7,520 miles, just 5% smaller than Earth's. Its mass is about 82% of Earth's, and its density and gravity are also quite similar. If you could stand on its surface, you'd weigh almost the same as you do on Earth. Venus orbits at about 0.72 AU from the Sun, equivalent to 108 million kilometers, 67 million miles. This is closer than Earth, but not close enough on its own to explain its incredibly high temperatures. The reason for Venus's catastrophic conditions lies in its unique atmosphere. Venus's atmosphere is one of the most extreme in the solar system. It's composed of about 96.5% carbon dioxide, with small amounts of nitrogen and trace sulfur compounds. The upper atmosphere is shrouded in thick clouds of sulfuric acid that reflect most sunlight. This reflectivity makes Venus appear so bright in our night sky. Its clouds bounce back about 70% of incoming solar radiation. Beneath these clouds, the surface atmospheric pressure is a crushing 92 times greater than Earth's at sea level. This is equivalent to the pressure found nearly 1 kilometer, over half a mile, beneath the ocean on Earth. Any base we tried to build there would be instantly crushed. The surface of Venus is the hottest of any planet in the solar system, with temperatures reaching a searing 470 to 878 degrees. This is hotter even than Mercury, despite Venus being farther from the Sun. The primary reason is a runaway greenhouse effect that completely transformed the planet's atmosphere and climate. It's believed that Venus may have once had more Earth-like conditions. Perhaps it even had liquid water on its surface. However, its proximity to the Sun played a critical role. Due to higher solar radiation, temperatures began to rise, water evaporated, and water vapor, a potent greenhouse gas, amplified the heat-trapping effect. Simultaneously, carbon dioxide, likely released through intense volcanic activity, built up in the atmosphere, increasing its density and exacerbating the greenhouse effect. Venus's atmospheric peculiarities define the planet's dynamics. Surprisingly, despite the intense sunlight reaching Venus, about 70% is reflected back into space. But the 30% that penetrates is absorbed by the surface and then trapped by the thick carbon dioxide blanket, unable to escape back into space. This process turns Venus into a thermal trap. The temperature on Venus is remarkably uniform across the entire surface, with minimal variation between day and night, or between the equator and the poles. This is due to the dense atmosphere, which efficiently distributes heat around the planet. Even at night, when the surface isn't illuminated by the sun, the temperature remains nearly as high as during the day. Beneath the clouds, Venus hides a fascinating world. The planet's surface has been mapped using radar, as optical methods are useless due to the thick cloud cover. Venus is a world of volcanoes. Its surface is almost entirely covered by vast lava plains formed by past eruptions. One of the highest points is Maxwell Montes, a mountain range rising to about 11 kilometers, nearly 7 miles, taller than Mount Everest. However, most of Venus's surface is relatively flat, marked by strange geological features like corona, large circular structures formed by upwelling magma. These coronae are remnants of powerful tectonic processes that occurred billions of years ago. Despite the evidence of volcanoes and lava flows, Venus shows no clear signs of Earth-style plate tectonics. Instead, its crust seems to bend and fracture under pressure from below, creating unique landforms. At altitudes around 60 km, 37 miles, incredibly powerful winds blow at speeds up to 360 km/h, 224 mph. This phenomenon is called superrotation. The atmosphere circles the planet much faster than the solid body rotates. Venus itself rotates incredibly slowly, taking 243 Earth days to complete one turn on its axis, the slowest rotation of any planet. Meanwhile, its year lasts only 225 Earth days. Remarkably, a day on Venus, specifically its sidereal day, is longer than its year. Venus was one of the first planets studied by spacecraft. The Soviet Venera missions were the first to send probes to its surface. Landers, like Venera 7, transmitted data from the surface, but survived only for about 30 minutes due to the extreme heat and pressure. More recently, the European Space Agency's Venus Express mission studied the atmosphere and planetary dynamics, including cloud chemistry. Today, new missions are planned, such as NASA's Da Vinci and Veritas, which will study Venus's terrain and internal structure. These missions could help answer the question, could Venus have been habitable in the past? Next in line is our home planet, Earth. We'll explore what makes it unique, and so far, the only known haven for life. The key feature that distinguishes Earth among other planets is the presence of liquid water. About 71% of our planet's surface is covered by oceans, seas, and rivers. Water is the foundation of life as we know it. Its unique properties, like high heat capacity and ability to dissolve substances, make it ideal for supporting biological processes. But why does Earth have liquid water, while Venus and Mars, for example, do not, at least on the surface? The secret lies in the planet's location. Earth resides in the so-called habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. If Earth were slightly closer to the Sun, it might have suffered Venus's fate. If it were farther away, it could have become a cold desert like Mars. Equally crucial is the magnetosphere, the magnetic field that shields our planet from harmful solar wind and cosmic radiation. Generated by the movement of molten iron in Earth's outer core, the magnetosphere acts like an invisible shield. Without it, the solar wind could strip away our atmosphere, as likely happened to Mars. Let's quickly define the solar wind. It's a stream of charged particles constantly emitted by the sun from its hot outer layer, the corona. These particles travel at speeds up to 800 km/h, about 500 miles, spreading throughout the solar system. The solar wind interacts with planets, causing various phenomena. On Earth, for instance, it creates the auroras, northern and southern lights, and interacts with our protective magnetosphere. Earth is a dynamic planet, its surface constantly changing, thanks to plate tectonics. The Earth's crust is divided into several large and small tectonic plates that float on the semi-fluid mantle beneath. These plates move, collide, separate, and slide under one another, creating mountains, ocean trenches, and earthquakes. Plate tectonics plays a crucial role in the planet's chemical cycles. For instance, carbon dioxide released by volcanoes helps maintain the greenhouse effect needed to retain heat. Furthermore, plate movement contributes to the renewal of the Earth's crust, supporting the planet's long-term stability. Geological processes like volcanism, despite their destructive power, also supply new materials to the Earth's surface. They release gases like carbon dioxide and water vapor, influencing the climate and minerals that enrich the soil. Earth's atmosphere is another unique feature, its composition perfectly suited for supporting life. Its main components are nitrogen, about 78%, and oxygen, about 21%, with small amounts of carbon dioxide, argon, and other gases. This balance isn't accidental. It was shaped by billions of years of biological and geological processes. oxygen appeared in the atmosphere thanks to ancient microbes that began producing it through photosynthesis. This transformation, known as the Great Oxidation Event, occurred about 2.4 billion years ago and fundamentally changed the planet's chemistry, making it suitable for complex life. Carbon dioxide, though a small fraction of the atmosphere, plays a vital role. It regulates the planet's temperature via the greenhouse effect, preventing Earth from freezing over. This delicate balance not only provides comfortable conditions for life, but is also vulnerable. Significant changes in carbon dioxide concentration could lead to climate catastrophes, reminiscent of what happened on Venus. Speaking of our planet, we can't forget its faithful companion, the Moon. The Moon is more than just a beautiful object in the night sky. It plays a critical role in Earth's stability and the development of life. The Moon's diameter is about 3,474 kilometers, 2,159 miles, making it the largest moon relative to its host planet's size in the solar system. First, the Moon stabilizes Earth's axial tilt. Thanks to the Moon, this tilt remains relatively constant, ensuring stable seasons and climate. Without the Moon, Earth's axis might wobble more dramatically, leading to severe climate shifts. Second, the Moon causes tides. These cyclical movements of water in oceans, seas, and even large lakes not only affect coastal ecosystems, but also likely played an important role in the evolution of life. Some scientists suggest tides might have helped life transition to land by providing environments where organisms could adapt to varying conditions. Third, the Moon served as a cosmic shield for Earth, absorbing impacts from asteroids and meteoroids, especially during the early history of the solar system. Without it, our planet's surface might be far more heavily cratered. Understanding Earth not only reveals its uniqueness, but also teaches us to appreciate the fragility of our home. The next planet we'll visit is Mars, our neighbor, which might tell us about Earth's past and potential future. Mars, the red planet, has captivated human imagination since ancient times. Its reddish hue in the night sky inspired myths and associations with war and destruction. But today, Mars symbolizes not war, but hope. It has become a window into the solar system's past and, perhaps, humanity's future. Let's explore why Mars holds such fascination. Mars is the fourth planet from the Sun, orbiting at an average distance of 228 million kilometers, 142 million miles, which is about 1.52 AU. This makes it roughly 1.5 times farther from the Sun than Earth, meaning it receives significantly less heat and sunlight. In terms of size, Mars has roughly half the diameter of Earth, but its surface area is comparable to Earth's total land area. Mars has only about 11% of Earth's mass, and its surface gravity is about 38% of Earth's. This means if you weigh 70 kilon, 154 lbs on Earth, you'd weigh only about 26 kilon, 59 lbs on Mars. Mars is mostly a cold, frozen desert. The average temperature on the planet is a chilly 83 degrees, 81 degrees. However, depending on the season and location, temperatures can range from 125 degrees, 193 degrees, at the poles in winter to a relatively mild 120 degrees, 68 degrees, near the equator in summer. These sharp fluctuations are due to its thin atmosphere, which does little to retain heat. Mars's thin atmosphere has a pressure only about 0.6% of Earth's at sea level. This is equivalent to the conditions found at an altitude of 30 kilometers, 19 miles above Earth's surface, 3 times higher than commercial airplanes fly. It's composed of about 96% carbon dioxide, with small amounts of nitrogen, argon, and trace amounts of oxygen and water vapor. One of Mars's most striking features is its potential for planet-encircling dust storms. These storms can lift fine dust high into the atmosphere, obscuring sunlight and making the planet even colder. The largest recorded storm in 2018 lasted for months and led to the end of the Opportunity rover's mission. Still, the Martian surface is incredible. Wastelands covered in iron oxide, rust, massive volcanoes, ancient dried-up riverbeds, and polar ice caps tell the story of a planet that might once have been very different. Imagine Olympus Mons, the tallest volcano in the solar system, standing 22 kilometers, nearly 14 miles high. That's almost 3 times the height of Mount Everest. And its base is so vast you couldn't see the summit from the ground. Or consider Valles Marineris, a vast canyon system stretching 4,000 km, 2,500 miles long, and up to 7 km, 4 miles deep. That's 10 times longer and 4 times deeper than the Grand Canyon. Scientists believe these features were likely formed by tectonic processes and perhaps massive water flows that once coursed across Mars. Yes, water is key to the Martian mystery. There's no liquid water on the surface today, but evidence of its presence in the past is everywhere. Billions of years ago, Mars was likely warmer and had a thicker atmosphere. Rivers flowed, lakes formed, and possibly even an ocean covered a significant portion of its surface. Today, water on Mars exists mainly as ice in the polar caps and beneath the surface. However, there's speculation that subsurface lakes of liquid water might exist, particularly near the South Pole. These findings offer hope that life could have existed on Mars in the past, or perhaps even persists today in hidden niches. Mars is currently the primary target for robotic exploration. Rovers like Curiosity and Perseverance continue to investigate the surface, gathering data on climate, soil composition, and searching for signs of ancient life. Curiosity, operating since 2012, confirmed that Mars once had conditions suitable for life. Perseverance, which arrived in 2021, is exploring Jezero Crater, the site of an ancient lake and river delta where microbial life might have thrived. But our ambitions don't stop there. Elon Musk and his company SpaceX aim to send humans to Mars in the coming decades, with the goal of establishing the first human settlements there. Our next stop takes us beyond the rocky inner planets to Jupiter, the king of planets, revealing a completely different kind of cosmic world. Our journey through the solar system continues, leaving the realm of rocky planets and venturing into the domain of the giants. Between Mars and Jupiter lies the asteroid belt, a region filled with millions of rocky and metallic objects that never coalesced into a full-fledged planet, likely due to the immense gravity of Jupiter, the most massive object in our system after the Sun. And the first giant we encounter is Jupiter, the most massive and enigmatic planet in the solar system. It's so large that over 1/300 Earths could fit inside it. Its influence extends far beyond its orbit. This gas colossus not only governs the paths of its many moons, but also acts as a kind of cosmic vacuum cleaner or shield, attracting asteroids and comets that might otherwise threaten the inner planets, including Earth. Jupiter is a world of raging storms, colossal pressures, crushing gravity, and a magnetic field stretching millions of kilometers into space. It's famed for its enduring Great Red Spot, spectacular auroras, and 4 large moons, each a potential world in its own right. Its mass is over 318 times that of Earth. But if it were to gain significantly more mass, it wouldn't necessarily get much bigger. At a certain point, under its own immense gravity, it would actually start to compress, becoming denser. Its surface gravity at the cloud tops is about 2.5 times stronger than Earth's. So, if a person could somehow stand on Jupiter, they'd weigh 2.5 times more. Of course, standing isn't possible. It doesn't have a solid surface. Jupiter is composed mainly of hydrogen and helium, much like the Sun. Descending through its outer clouds, you'd travel through layers of increasingly dense gas. First, an atmosphere filled with swirling ammonia and methane clouds, featuring hurricanes larger than Earth, then deeper where hydrogen becomes liquid, and deeper still, it transitions into metallic hydrogen, a substance only achievable in labs on Earth under extreme pressure. This vast ocean of metallic hydrogen, potentially tens of thousands of kilometers deep, behaves like a metal and conducts electricity. It's here that Jupiter's incredibly powerful magnetic field is generated, extending millions of kilometers around it. What lies even deeper? Possibly a small, dense core roughly the size of Earth, perhaps up to 10-15 times Earth's mass, composed of rock and ice. Scientists are still debating its exact nature. It's possible the immense pressure has caused the core to partially dissolve into the surrounding metallic hydrogen. Jupiter wouldn't be Jupiter without its turbulent atmosphere, covered in distinctive bands. These light-colored zones and dark-colored belts are the result of powerful jet streams moving in opposite directions at speeds up to 640 km/h, 400 km/m. The entire atmosphere is a turbulent ocean of gas where constant vortices create intricate patterns. Lightning flashes thousands of times brighter than on Earth, and pressure in the lower layers likely compresses gas into liquid states. And of course, there's the Great Red Spot. This gigantic storm is a true veteran among tempests, having been observed raging for at least 350 years. Its diameter is currently about 16,000 kilometers, 10,000 miles, more than enough to swallow Earth, though it has been slowly shrinking over recent decades. Scientists aren't sure if it will eventually disappear, but this storm remains one of the most spectacular phenomena in the solar system. Jupiter's magnetic field is the most powerful of any planet, nearly 20,000 times stronger than Earth's. It creates an enormous magnetosphere, so vast that if it were visible from Earth, it would appear larger in the sky than the full moon. The environment around Jupiter is intensely radioactive. Streams of charged particles race around the planet, making the radiation levels near Jupiter lethal, even for heavily shielded spacecraft. This is why missions like Juno must execute complex orbits to minimize exposure to the most dangerous zones. Jupiter isn't just the gas giant itself. It also reigns over a system of 95 confirmed moons as of late 2023. The most famous are the 4 Galilean moons discovered by Galileo Galilei: Io, Europa, Ganymede, and Callisto. Each is a unique world. Io is a volcanic hellscape, the most geologically active body in the solar system. Volcanoes constantly erupt, spewing sulfur compounds that paint its surface bright yellow and orange. Its interior is heated by the constant gravitational tug-of-war between Jupiter and the other large moons. Europa is an ice-covered world. Beneath its icy crust, several kilometers thick, lies a vast ocean of liquid water, containing more water than all of Earth's oceans combined. The surface is crisscrossed with cracks caused by Jupiter's tidal forces, and evidence suggests plumes of water vapor may erupt into space. If life exists elsewhere in the solar system, Europa is a prime candidate. Ganymede is the king of moons. Larger than the planet Mercury, it's the biggest moon in the solar system and the only one known to have its own magnetic field. Its surface features a mix of dark, ancient, cratered terrain and younger, brighter, grooved terrain. It too may harbor a subsurface ocean. Callisto is an ancient, heavily cratered world. It's one of the oldest surfaces in the solar system, having changed little over billions of years. Like Ganymede and Europa, it might also conceal a hidden ocean beneath its icy crust. Jupiter was the first outer planet studied up close. The Pioneer and Voyager spacecraft flew past in the 1970s, but the most detailed studies came from the Galileo orbiter in the 1990s and the ongoing Juno mission. Future exploration promises to be even more exciting. In the 2030s, the European Space Agency's JUICE, Jupiter Icy Moons Explorer mission, will arrive to study Ganymede, Callisto, and Europa, seeking to determine if their oceans could harbor life. NASA's Europa Clipper mission will also perform detailed reconnaissance of Europa. Jupiter is undoubtedly the king of planets, but its neighbor Saturn is no less astonishing. It's a world that embodies alien beauty, adorned with the greatest ring system in the solar system and hosting the moon Titan, with lakes of liquid methane on its surface. What secrets does this enigmatic planet hold? Leaving Jupiter, our path leads further out to Saturn, arguably one of the most beautiful planets in the solar system. If Jupiter is the king in terms of size and power, Saturn is its majestic sibling, adorned with the most stunning ring system, making it truly one of a kind. Saturn is the second largest planet in the solar system. Its diameter is about 9.5 times that of Earth. However, despite its enormous size, Saturn is the least dense planet. Its average density is less than water, meaning if you could find an ocean large enough, Saturn would float in it. But of course, its defining feature is its magnificent rings, which have made it one of the most recognizable planets. When we look at photos of Saturn, the rings appear solid and continuous, like a giant disk. But this is an optical illusion. In reality, they are composed of billions of particles of ice and rock orbiting the planet. These particles range in size from tiny dust grains to chunks as large as houses. The rings are incredibly thin compared to their width, averaging only about 10 meters, 30 feet, thick, while their diameter spans hundreds of thousands of kilometers. Essentially, they form a gigantic, flat disk, so thin it practically disappears when viewed edge-on. Scientists still debate the ring's origin. Several hypotheses exist. Perhaps they are the remnants of a moon that strayed too close to Saturn and was torn apart by its gravity. Or maybe they are material that failed to coalesce into a moon due to the planet's gravitational influence. The rings contain fascinating structures, like the Cassini division, a large gap about 4,800 kilometers, 3,000 miles wide, separating the A and B rings. This gap is primarily maintained by the gravitational influence of Saturn's moon Mimas, which clears particles from this region. Like Jupiter, Saturn's atmosphere is mostly hydrogen and helium, with traces of other gases that give the clouds yellowish and golden hues. But while Jupiter's great red spot captures most attention, Saturn boasts an equally mysterious feature, a hexagonal storm at its north pole. This structure is a true scientific marvel. Imagine a giant storm about 25,000 kilometers, 15,500 miles across, maintaining a remarkably stable, geometrically perfect hexagonal shape. Inside this storm, winds rage at speeds over 500 km/h, 310 mph, yet its sides remain astonishingly straight, as if drawn with a ruler. Scientists are still working to understand why this storm maintains such a shape. This isn't the only atmospheric phenomenon on Saturn. In 2010, its northern hemisphere noticeably changed color from bluish to golden. This change was likely due to photochemical reactions triggered by increased sunlight as summer arrived in that region. Ultraviolet light altered molecules in the upper haze layers, shifting the apparent color. But Saturn is more than just the planet and its rings. It also commands a system of 83 confirmed moons as of late 2023, among which Titan stands out. It's one of the most intriguing objects in the solar system. Titan is the second largest moon after Ganymede. It's larger than the planet Mercury and is the only moon known to have a dense atmosphere. This atmosphere makes it exceptionally special. If you were standing on Titan's surface, the sky above would be a hazy orange, and surrounding you would be plains covered in frozen hydrocarbons. And the strangest part? It rains on Titan, but not water, liquid methane and ethane. The temperature here is about 180 degree, 294 degree, so water is frozen solid like rock. Instead, rivers, lakes, and seas are composed of liquid hydrocarbons, which remain fluid at these frigid temperatures. In some ways, this world bears a striking resemblance to early Earth. It has seasons, clouds, precipitation, and its lakes and rivers change with the time of year. We observe some methane seas gradually evaporating, while new bodies of liquid appear elsewhere. Perhaps most intriguingly, deep beneath Titan's surface, an ocean of liquid water might exist. If so, conditions suitable for life could potentially be found there. While Titan captivates with its dense atmosphere, another Saturnian moon, Enceladus, stuns with its geysers. Enceladus is a small world, only about 500 kilometers, 310 miles in diameter, but it's incredibly active. The Cassini spacecraft discovered plumes of water vapor and ice particles erupting from its south pole into space, forming vast clouds. These geysers are so powerful they feed Saturn's E-ring. Beneath Enceladus's icy surface lies an ocean of liquid water. Analysis of the plumes has revealed organic molecules and evidence of chemical reactions that could potentially provide energy for life. This makes Enceladus, alongside Europa, a top candidate in the search for extraterrestrial life within our solar system. The most detailed exploration of Saturn and its moons was carried out by the Cassini-Huygens mission. Launched in the late 1990s, the spacecraft spent 13 years in the Saturn system, transmitting thousands of images and invaluable scientific data. The Huygens probe, released from Cassini, successfully landed on Titan in 2005, becoming the first probe to land on a moon in the outer solar system. It sent back images of the orange haze, rocky plains, and evidence of ancient river channels. In 2017, Cassini ended its mission with a planned plunge into Saturn's atmosphere, transmitting data until the very last moment. Saturn is the last of the gas giants, but beyond it lie Uranus and Neptune, ice giants that hold just as many mysteries. They boast incredibly powerful winds, strange magnetic fields, and moons that might hide subsurface oceans. After exploring Saturn's domain, our journey continues deeper into the solar system, entering the realm of the ice giants. Uranus, the seventh planet from the Sun, may be smaller than Jupiter and Saturn, but it astounds with its uniqueness. It seems to break all the rules. Pale blue-green, enigmatic, spinning on its side, and encircled by faint rings and moons with bizarre terrains. Its cold, seemingly placid atmosphere hides secrets that remain largely unexplored. Like Jupiter and Saturn, Uranus is a giant planet, but with a key difference. While the two largest planets are primarily hydrogen and helium, Uranus and its neighbor Neptune belong to a different category: ice giants. What does this mean? Uranus contains much higher proportions of heavier elements, often referred to as ices, like water, ammonia, and methane. Instead of hot metallic hydrogen deep inside like Jupiter, Uranus likely has a vast, hot, dense fluid mantle composed primarily of these icy materials. If you could descend into Uranus's atmosphere, you'd first pass through upper clouds of methane ice overlaying deeper layers possibly made of ammonia and hydrogen sulfide ice, all above a thick atmosphere of hydrogen and helium. As pressure increases, the gases would compress, transitioning into that hot, dense fluid mantle. If you ask whether Uranus has a solid surface to stand on, the answer is no. The atmosphere gradually transitions into the deeper layers, and the closest thing to a surface might be defined by a specific pressure level. perhaps similar to Earth's surface pressure. At the center of Uranus, there likely lies a small rocky core about the size of Earth, surrounded by that thick, hot, icy mantle. Temperatures inside might reach 5,000 degrees, 9,000 degree current, but due to the insulating layers above, very little of this internal heat escapes. In fact, Uranus is the coldest planet in the solar system, with minimum temperatures in its upper atmosphere reaching 224 degrees, 301 degrees, even colder than the more distant Neptune. Why? Uranus radiates very little internal heat compared to the other giants, which are still gradually releasing energy from their formation. Uranus's most astonishing feature is its bizarre rotation. Unlike all other planets, which spin more or less upright relative to their orbits, Uranus is tilted on its side by about 98 degrees. This means it essentially rolls along its orbital path, with its poles alternately pointing almost directly towards or away from the Sun. This results in the most extreme seasons in the solar system. While Earth experiences seasonal changes every few months, on Uranus, one pole faces the Sun for 42 consecutive years, followed by 42 years of complete darkness for the other pole. Why is it tilted like this? Scientists believe that early in its history, Uranus was struck by a massive object, perhaps an Earth-sized protoplanet. This colossal impact likely knocked it onto its side, resulting in its unique rotation. Although Uranus often appears as a featureless blue-green ball, its atmosphere is actually quite dynamic. It's composed mainly of hydrogen and helium, with about 2% methane. It's this methane that gives Uranus its pale blue-green color, as it absorbs red light and reflects blue and green wavelengths. Extremely strong winds blow on Uranus, reaching speeds up to 900 km/h, 560 mm/h. Occasionally, giant storms can appear as bright clouds in its atmosphere, though they are less prominent than on Jupiter or Neptune. While Saturn is famous for its rings, Uranus has them too. They are much fainter and darker than Saturn's, composed of particles that reflect very little light. But some of the real wonders lie among its 27 known moons. The most peculiar is Miranda. This moon looks like it was shattered and haphazardly reassembled, with giant canyons, towering cliffs, some potentially the tallest in the solar system, and wildly varied terrains jumbled together across its surface. Scientists speculate that Miranda might have been destroyed by a massive impact long ago, only for its fragments to eventually pull themselves back together into this chaotic world. To date, the only spacecraft ever to visit Uranus was Voyager 2 during its flyby in 1986. It flew past the planet, providing the first and only close-up images we have. No other probe has visited since, but scientists are strongly advocating for a new mission, potentially launching in the 2030s or 2040s. NASA is considering an orbiter mission that could study Uranus's atmosphere, rings, moons, and internal structure in detail. After the icy and enigmatic Uranus, our journey reaches the last of the known giant planets, Neptune. This is the most distant planet, the windiest, and perhaps the most mysterious. Even today, despite powerful telescopes and sophisticated computer models, Neptune remains one of the least explored planets. first glance, it resembles Uranus, another blue-hued sphere veiled in clouds, but the differences quickly become apparent. While Uranus appears serene and is colder externally in its upper atmosphere, Neptune is a dynamic, stormy giant, home to the fastest winds in the solar system. This planet is the true master of cosmic winds, and its story is filled with intrigue. Neptune is an ice giant, like Uranus, but its atmosphere is much more dynamic and visually active. Composed mainly of hydrogen, helium, and methane, it has a similar deep blue color to Uranus, likely enhanced by an unknown atmospheric component. But the defining feature is its winds. Neptune's atmosphere hosts the most extreme winds in the solar system. With speeds reaching an astonishing 2,100 km/h, 1,300 mph. That's faster than the speed of sound on Earth, and far stronger than the most powerful hurricanes here. Scientists are still trying to fully understand how Neptune, so far from the Sun, sustains such a turbulent atmosphere. The planet receives only about 1/900th the solar energy Earth does, and its upper cloud layers are frigid, yet deeper down, a maelstrom of storms and vortices rages. Neptune also featured its own giant storm, the Great Dark Spot. When Voyager 2 first imaged Neptune in 1989, scientists saw a massive dark vortex, similar in relative size to Jupiter's Great Red Spot. It spanned thousands of kilometers, with winds inside estimated at near supersonic speeds. But when the Hubble Space Telescope observed Neptune a few years later, the spot had vanished. It simply dissipated. Since then, other dark spots, new giant storms, have been observed appearing and disappearing in Neptune's atmosphere every few years. This makes Neptune unique among the gas giants, where huge storms are transient phenomena rather than centuries-long features. Like Uranus, Neptune lacks a solid surface. Anyone attempting to land would simply sink deeper into the gas layers until crushed by the immense pressure. Compared to Jupiter and Saturn, Neptune, like Uranus, contains a higher proportion of ices, water, ammonia, and methane. Beneath its thick atmosphere lies a deep, hot, dense mantle, likely composed of these materials in a fluid state. Below this mantle is believed to be a core of rock and ice, roughly the mass of Earth. Temperatures at Neptune's center could reach 7,000 degrees Celsius, 12,600 degrees Celsius. This hot core likely contributes significantly to Neptune's atmospheric activity, as the planet radiates more than twice the energy it receives from the Sun. Among Neptune's 14 known moons, Triton stands apart. It's the planet's largest moon and one of the strangest objects in the solar system. Triton's most notable feature is its retrograde orbit. It orbits Neptune backwards, compared to the planet's rotation and the orbital direction of most other large moons. This strongly suggests Triton wasn't formed with Neptune, but was likely a dwarf planet captured from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. But the peculiarities don't end there. Triton's surface is covered in frozen nitrogen, methane, and carbon dioxide ice, and its surface temperature is about 235 degrees, 391 degrees, making it one of the coldest known places in the solar system. Perhaps most surprising is the evidence of cryovolcanism, or ice geysers. Voyager 2 detected dark plumes rising several kilometers above the surface, likely composed of nitrogen gas and dust erupted from below. This implies there's an internal heat source warming the subsurface ice, potentially even maintaining a liquid water ocean beneath the icy crust, similar to Europa and Enceladus. Currently, the only spacecraft to have ever visited Neptune is Voyager 2 during its 1989 flyby. No probes have been sent specifically to Neptune since, but astronomers are actively discussing potential future missions. Concepts like Neptune Odyssey envision an orbiter studying the planet in detail. NASA has also considered missions like Trident, which would specifically target Triton to investigate the hypothesis of a subsurface ocean. However, such missions would take decades. Even if launched in the near future, a probe would likely reach Neptune no earlier than the 2040s. Our tour of the planets in the solar system is complete, but the system itself doesn't end here. Beyond Neptune lies the Kuiper Belt, hiding thousands of icy worlds like Pluto, Haumea, Makemake, and Eris. We've covered all 8 planets, but between them and far beyond stretches a whole realm of smaller bodies: asteroids, comets, dwarf planets, and meteoroids. These objects might seem insignificant compared to giants like Jupiter or Saturn, yet their role in the formation and evolution of the solar system is immense. They hold clues about its distant past, and some even pose a potential threat to Earth. When astronomers first began systematically observing the sky, guided by orbital dynamics calculations, they expected to find another planet between Mars and Jupiter. Instead of one planet, they discovered the asteroid belt, a zone filled with millions of small, rocky, and metallic objects that never managed to form a full-sized planet, primarily due to Jupiter's powerful gravitational influence. Asteroids come in various sizes, from giants like Vesta, about 525 kilometers, 326 miles in diameter, down to tiny fragments just a few meters across. They are composed of rock, metals, carbon compounds, and some even contain water ice. Beyond their scientific value, asteroids pose a potential threat to Earth. We know that about 66 million years ago. A large asteroid impact contributed significantly to the extinction of the dinosaurs. Today, astronomers carefully track potentially hazardous asteroids, PHAs, whose orbits might cross Earth's path. While the largest known PHAs currently pose no immediate danger, smaller objects could still present a threat. That's why NASA and other space agencies are developing planetary defense strategies, including missions like DART, Double Asteroid Redirection Test, which successfully altered the orbit of a small asteroid moonlet in 2022. For a long time, Pluto was considered the 9th planet of the solar system. But in 2006, the International Astronomical Union reclassified it as a dwarf planet. This sparked considerable debate, as Pluto remained a beloved planet for many. But why the demotion? The main reason is that Pluto hasn't cleared its neighborhood, meaning it doesn't gravitationally dominate its orbital zone, sharing it with other sizable objects. These neighbors, like Haumea, Makemake, and Eris, also reside in the Kuiper Belt, a vast region beyond Neptune filled with icy bodies, remnants from the solar system's formation. Despite its reclassification, Pluto remains a fascinating world. It has 5 known moons, the largest being Charon, which is so large relative to Pluto that they form a binary system, orbiting a common center of mass outside Pluto itself. Its surface features vast plains of nitrogen ice, towering mountains of water ice, and signs of geological activity, including possible cryovolcanoes, ice volcanoes. When the New Horizons spacecraft flew past Pluto in 2015, it sent back images that stunned scientists. This small, distant world turned out to be far more complex and active than expected. While asteroids are primarily rock and metal, comets are often described as dirty snowballs, mixtures of ice, water, carbon dioxide, methane, ammonia, dust, and organic molecules. As they approach the sun, they heat up, and the ices sublimate, turn directly from solid to gas, forming a glowing cloud called a coma around the nucleus, and often long tails of gas and dust. These tails always point away from the sun, pushed by solar radiation pressure and the solar wind. Comets originate from 2 main regions: the Kuiper Belt, the source of most short-period comets like the famous Halley's Comet, returning roughly every 76 years, and the Oort cloud, a vast spherical shell at the very edge of the solar system, thought to be the origin of long-period comets like Comet Hale-Bopp. Comets may have played a key role in Earth's history. Some scientists believe they delivered a significant portion of Earth's water and perhaps even the organic molecules necessary for life to begin. And what about meteoroids, meteors, and meteorites? Meteoroids are small fragments of asteroids or comets orbiting the sun. When a meteoroid enters Earth's atmosphere, friction causes it to heat up and glow, creating a streak of light we call a meteor, or shooting star. Most burn up completely. If any piece survives the fiery descent and hits the ground, it's called a meteorite. The most famous recent example is the Chelyabinsk meteor, which entered the atmosphere over Russia in 2013, creating a powerful shock wave that shattered thousands of windows. Our journey through the solar system's planets and smaller bodies has reached its end. But when you think about it, everything we've seen, from tiny Mercury to distant Neptune, exists only thanks to one object. Without it, there would be no heat, no light, no stable orbits, and no life as we know it. That object is the Sun, our stellar powerhouse, around which the entire system revolves. The Sun is a star. It's not just a hot ball of gas, but a complex and dynamic body where nuclear fusion reactions take place in its core, generating a colossal amount of energy. It's so enormous that its mass accounts for over 99.8% of the total mass of the solar system. That means all the planets, moons, asteroids, and comets combined weigh less than 1/5 of 1% of the Sun's mass. But what is this giant luminary actually like? What processes occur within it, and how does it influence our planet and the entire system? Let's find out. The Sun appears to us as a solid, shining sphere, but it's actually composed of several distinct layers, each playing a role in generating and transporting energy. The core. This is the Sun's center, where the most crucial processes happen. temperatures reach about 15 million degrees Celsius, 27 million degrees, and the pressure is immense, about 250 billion times Earth's atmospheric pressure at sea level. It's under these extreme conditions that thermonuclear fusion occurs, the process where hydrogen atoms fuse to form helium, releasing tremendous amounts of energy. The radiative zone. In this next layer out, the energy generated in the core slowly travels outward. Unlike the core, things are relatively calmer here. Energy is transported primarily by photons, particles of light. A photon born deep within the sun can take hundreds of thousands of years to randomly bounce its way through this dense layer before reaching the next zone. The convective zone. Here, energy transport changes. Instead of photons slowly diffusing outwards, hot plasma rises, cools as it nears the surface, and then sinks back down, much like boiling water in a pot. These powerful convection currents are responsible for the granular patterns and sunspots we observe on the sun's surface. The photosphere. This is the visible surface of the sun, the layer we see from Earth. On the scale of the sun, it's a very thin layer, only about 500 kilometers, 300 miles thick, but it's the layer that emits most of the light that warms and illuminates our planet. The photosphere's temperature is about 500 degrees, 10,000 degrees, relatively cool compared to the core. The chromosphere and corona. These are the sun's outer atmosphere. The chromosphere is a layer above the photosphere, visible during solar eclipses as a reddish glow. The corona is the outermost layer, an incredibly hot, millions of degrees, and tenuous halo of plasma that extends millions of kilometers into space. It's also most easily seen during a total solar eclipse. The sun is an active, dynamic star, constantly undergoing powerful events that impact the entire solar system. The main engine is thermonuclear fusion. In the core, about 600 million tons of hydrogen are converted into helium every single second, releasing energy equivalent to the detonation of billions of hydrogen bombs every second. This process provides the outward pressure that balances the sun's immense gravity, keeping it stable and allowing it to shine for billions of years. But the sun isn't always calm. Powerful releases of energy sometimes occur on its surface. Sunspots. These are temporary dark patches on the photosphere that are cooler than their surroundings, caused by intense magnetic activity. Solar flares. These are sudden, intense bursts of radiation erupting from the sun's surface, often associated with sunspots. They release huge amounts of energy across the electromagnetic spectrum. Coronal mass ejections, CMEs. These are even more powerful events, enormous eruptions of billions of tons of plasma and magnetic fields from the sun's corona, traveling outwards at speeds of hundreds or even thousands of kilometers per second. If flares or CMEs are directed towards Earth, they can cause geomagnetic storms, disrupting satellite communications, navigation systems, and power grids, as well as creating spectacular auroras. Despite the vast distances to the outer planets, the Sun's influence is felt throughout the entire system via three main mechanisms: gravity, radiation, and the solar wind. Gravity. The Sun's immense gravity holds all the planets, asteroids, and comets in their orbits. Without it, everything would fly off into interstellar space. Its gravity has kept our system stable for billions of years. Radiation. Solar radiation, light and heat, provides Earth with the energy necessary for life. Without this radiation, our planet's surface would freeze, and the atmosphere would likely collapse into a lifeless, icy layer. Radiation pressure also affects the orbits of small particles and pushes comet tails. Solar wind. This continuous stream of charged particles flows outward from the Sun in all directions. It shapes planetary magnetospheres, influences atmospheres, creates auroras, and pushes the gas tails of comets. The outermost boundary of the Sun's influence is the heliopause, where the solar wind pressure balances with the pressure of the interstellar medium, the gas and dust between stars. This boundary lies billions of kilometers from the Sun, marking the edge of its dominion and the beginning of interstellar space. The Sun formed about 4.6 billion years ago and will continue to shine steadily for about another 5 billion years. But it's not eternal. In about 5 billion years, it will exhaust the hydrogen fuel in its core and begin to evolve. It will expand dramatically, becoming a red giant. Its outer layers will swell, engulfing Mercury, Venus, and possibly even Earth. After several 100 million years in this phase, it will shed its outer layers, creating a beautiful planetary nebula, leaving behind its hot, dense core, a white dwarf, which will slowly cool over trillions of years. But that fate is billions of years away. For now, the Sun remains our ultimate source of life and energy, the anchor without which our solar system could not exist. We began our journey exploring the planets, but now it's clear. Everything in our system is interconnected through the Sun and its profound influence. It's an amazing, complex, and dynamic system where every planet, moon, and even the most distant comet is bound by the invisible threads of gravity, radiation, and energy from our star. Thank you for joining me on this fascinating journey through the vast expanse of our solar system. I hope this exploration has helped you learn something new, discover amazing facts, and perhaps look at the cosmos with even greater wonder. If you enjoyed our tour, feel free to share your thoughts, ask questions, and continue exploring the universe. Space is vast, and countless discoveries still await us.